Okay, so let's talk about what should happen if you don't have enough electrons. You need to take an unshared pair and change it to a shared pair. Let's see how that works with nitrogen. There are two nitrogens, each one has 5 valence electrons for a total of 10. You're going to connect each nitrogen using a line, that's 2. Then we would do 4, 6, 8, 10. You can see the nitrogen on the left has 8, just like it needs. The nitrogen on the right only has 4. Okay, we only have 10 electrons to work with. There's nothing we can do about the number of electrons. So this is where, like, watch this pair down here. I'm going to erase those dots. Of course, I accidentally erased my nitrogen too. And I'm going to change it to a line. Okay, so I'm still using 10, 2, 4, 6, 8, 10, right? But now this one has 8 and this one has 6, so we're getting closer. But you can see with nitrogen, we're not done. We're going to have to erase this pair of dots also over here on the left. Okay, so you're going to erase those dots. Change that to a line. Now we have 2, 4, 6, 8, 2, 4, 6, 8. We use 10 electrons total. Everybody's happy. Okay, so try CO2. All right, this is a good place to pause the video. Pause it if you want. Try CO2 on your own. Okay, and then we'll look at it together. All right, so hopefully you paused. Okay, so let's look at this. Carbon has 4. Each oxygen has 6. There are 2 oxygens. That's a total of 16 electrons. We're going to put carbon in the middle, oxygen on each side, 2, 4. Okay. Then I'm just going to start with the one on the left. It doesn't really matter. 6, 8, 10, 12, 14, 16. Okay. I just drew my structure. I accounted for 16 valence electrons, but you can see that there's a problem because carbon doesn't have 8, carbon only has 4. So what we're going to have to do is we're going to erase a pair off oxygen right here. Oops, I just erased the oxygen. And we're going to make that a line. Okay. Now, 2, 4, 6, 8, 2, 4, 6, 8. 2, 4, 6, we're getting closer. We're going to do the same thing on the other oxygen. We're going to do the same thing on the other oxygen so that now carbon has 8. There are 2 double bonds. It's possible that if you tried this one on your own, you drew a triple bond and a single bond, like a triple bond on one side, a single bond on the other. In a little bit, we're going to talk about why that might happen. And this is the better structure, and I'll show you why. Okay. All right. What if there are too many electrons and every Adams octet rule is met? Well, then you're going to have to place the extra electrons on the central atom to create what's called an expanded octet. Noble gases actually do this. Like xenon is a noble gas that is willing to bond. It just has to do it in a different way because it doesn't really need the pairs, but it'll expand its octet. Okay. And then fluorine, as you know, has 7. So that's 28 plus 8, that's 36. Okay. You're going to put xenon in the middle, and then you're going to attach 4 fluorines. Okay. So 2, 4, 6 in terms of electrons, 8, right? 2, 4, 6, 8. And then 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Those extra electrons go on xenon. And that is referred to as an expanded octet. Okay, so that's where those go. All right, draw ozone. Pause it for a minute and draw ozone, O3. See what you come up with, okay? All right, hopefully you paused it. Oxygen has 6. There are 3 of them, that's 18 total. You're gonna do O, connected to O, connected to O. Okay, so we've just drawn 4 electrons total. We're gonna do the outer oxygens first, same rules. 6, 8, 10, 12, 14, 16, 18. Okay, so the one in the middle doesn't have enough. We're gonna erase a pair and we're gonna do that. Okay, now some of you might be thinking, wait a second, that's not how I did it. The way that I did it was by putting the double bond over there on the right. And knowing you guys, you're probably thinking, is that wrong? Should I not have done that? Nope, you can do that. Those 2 structures are equally valid. They're called resonance structures. So resonance structures are when you have more than one acceptable and equally valid structure. Okay. And really, ozone exists as like a combination of these 2 structures. Like the double bond actually moves, and it would be considered really like to be a bond and a half, but we can't draw a bond and a half. So we draw the resonance structures to show that this bond kind of moves around and gets split in multiple places. Okay. All right. So you'll notice that I use this phrase equally valid, and you might be wondering, well, what does that mean? Okay. How do you know if the structure is equally valid compared to another structure? That is by assigning something called formal charge to an atom. Okay. Formal charge is when you count the number of valence electrons that that atom has, and you subtract the total of all the unshared electrons on that atom minus half the shared electrons. Okay. The best structure is the one where there's a formal charge of 0 in as many places as possible, or where the more negative formal charge is on the more negative or on the more electronegative atom. Okay. So we're going to look at CO2. Remember I said some of you might have drawn a triple and a single instead of 2 doubles. I'll show you how I know, and ignore it, like that black dot right there, ignore it. It's just on my board, but I don't think I can get rid of it. So just ignore that. Okay, so here's how this works, right? Oxygen has 6 valence electrons. Carbon has 4, and oxygen has 6, okay? All right. On this oxygen right here, it has 4 unshared electrons, and then it has 4 shared electrons, but you're only using half of those. Remember, it says you're going to subtract all the unshared electrons, so 1, 2, 3, 4, and half of the shared electrons, which is 2. Okay, so we're going to subtract 6. That's going to give this a charge of 0, or a formal charge of 0. You're going to do the same thing over here. 4, 5, 6, 0. Look at the carbon. It has 4. It has 4 shared pairs. So we're only 1, 2, 3, 4. We're only going to count 4 of those electrons. That gives a formal charge of 0. Okay. So you see, by using this structure, everything has a formal charge of 0. Let's look at this other structure to understand why this is not equally valid. Same number of valence electrons, right? Okay. So if you look at this oxygen over here, 1, 2, 3, 4, 5, 6, and then plus 1 from that shared pair is 7. So that gives a -1, right? Let's look at carbon. 1, 2, 3, 4. Okay, so that gives a 0. And then let's look at this oxygen. 1, 2, 3, 4, 5. That gives a charge of a formal charge of +1 on this oxygen. Okay, well, here's the thing, you guys. Both oxygens are equally electronegative. Okay, and remember in the rules it says you want this, like, if you want as many formal charges to be 0 as possible, But if they can't be zero, you want the more electronegative atom to have the negative formal charge. Well, so here it does, but here it has a positive charge, and it shouldn't, because it's just as electronegative as this one. So to have this situation doesn't make sense. This is the preferred structure because it has formal charges of 0 for everybody. Okay.